Pringles aren't made from potatoes. Well, they are, but not the way you think. That perfectly uniform chip isn't sliced from a potato. It's manufactured from a dough that's only 42% potato. The rest is corn flour, wheat starch, and a dozen other ingredients most people can't pronounce. And the process that turns this dough into identical stackable chips is so precise that every Pringle produced worldwide has exactly the same curve, the same thickness, and the same 14 ridges on its surface. Here's how Pringles are actually made, why they had to be engineered this way, and why the manufacturing process is more like building a car than cooking food. Pringles start as actual potatoes. But these aren't the fresh potatoes you buy at the grocery store. These are dehydrated potato flakes that arrive at the factory in massive 50-pound bags. The potatoes were harvested, peeled, sliced, cooked, and dehydrated at a separate facility specifically designed for potato processing. The dehydration happens through a process called drum drying. Fresh potatoes are cooked into a mash, spread thin on massive heated drums rotating at 120 degrees Celsius, and dried into flakes in under 30 seconds. The moisture content drops from 80% to 6%. What used to be 100 pounds of fresh potatoes becomes 20 pounds of dried flakes. This is why Pringles factories don't need massive refrigeration systems or deal with potato spoilage. They're working with shelf-stable ingredients that can sit in storage for months. But here's why this matters. Fresh potatoes are inconsistent. Different sizes, different moisture levels, different sugar content depending on where they were grown and when they were harvested. You can't manufacture identical chips from inconsistent raw materials. Dehydrating everything first creates a standardized ingredient that behaves predictably every single time. The factory receives potato flakes from multiple suppliers across different regions. These flakes are tested for moisture content, starch levels, and particle size. If a batch doesn't meet specifications within a tolerance of 0.5%, it's rejected. This level of precision is necessary because the dough-making process requires exact ratios. Too much moisture, and the dough is sticky. Too little, and it cracks during forming. The potato flakes enter a massive industrial mixer along with corn flour, wheat starch, maltodextrin, emulsifiers, and water. The ratio is precise, down to the gram. For every 100 pounds of final dough, 42 pounds is potato, 35 pounds is corn and wheat starches, 3 pounds is various binders and emulsifiers, and 20 pounds is water. This isn't cooking. This is material science. The corn flour provides structural integrity. The wheat starch controls how the chip absorbs oil during frying. The maltodextrin affects final texture and crispness. The emulsifiers ensure everything binds uniformly and the dough doesn't separate. Every ingredient serves a specific engineering purpose. The mixing happens in controlled atmosphere chambers with precise temperature and humidity controls. The mixture is blended for exactly 4 minutes and 20 seconds at 2,800 revolutions per minute. This specific timing and speed creates dough with the exact consistency needed for the next step. Mix too long, and you develop too much gluten from the wheat starch, making chips tough. Mix too short, and you get inconsistent texture. The dough that comes out looks like thick pizza dough. It's pale yellow, slightly sticky, and completely uniform. No variation. If you examined it under a microscope, you'd see that the starch granules are distributed evenly throughout. This is what 100 years of food engineering looks like. A product that started as chaotic organic material has been reduced to a perfectly controlled substance. The dough moves to sheeting rollers. These are massive steel cylinders that flatten the dough to exactly 1.5 millimeters thick. Not 1.4 millimeters. Not 1.6 millimeters. Exactly 1.5, with a tolerance of plus or minus 0.1 millimeters. Laser sensors measure the dough sheet constantly as it passes through. If any section falls outside the tolerance range, the entire sheet is rejected and recycled back into the mixer. The sheeting happens in multiple stages. The dough passes through 6 pairs of rollers, each one slightly closer together than the previous. This gradual reduction prevents the dough from tearing or developing weak spots. If you tried to flatten it in one step from 3 centimeters to 1.5 millimeters, you'd create stress fractures in the starch matrix that would show up as cracks after frying. Between each roller pair, the dough rests for exactly 8 seconds. This lets the gluten strands relax. Wheat starch develops some gluten when mixed with water, and gluten becomes springy when worked. The resting periods prevent the dough from springing back after being rolled. Without these pauses, you'd end up with chips that are thicker in some areas than others. The dough sheet emerges perfectly flat, perfectly uniform, and ready for cutting. It's moving at 12 meters per minute through the factory at this point. From potato flakes entering the mixer to dough sheet exiting the rollers takes exactly 8 minutes and 40 seconds. The entire operation is synchronized like a factory making precision parts, not snack food. Here's where Pringles become Pringles. The dough sheet feeds into a cutting and molding station where oval cutters punch out individual chip shapes. These cutters are arranged in a grid pattern that maximizes dough usage. The spacing is optimized so that 96% of the dough sheet becomes chips. Only 4% is scrap that gets recycled back into the mixer. But cutting alone doesn't create the Pringle shape. The oval cutouts are still flat. They move immediately to a molding station where they're placed onto saddle-shaped molds. These molds are heated to 70 degrees Celsius and have exactly 14 ridges pressed into their surface. The dough oval is pressed into the mold and held there for 1.2 seconds. This creates the hyperbolic paraboloid curve. That's the mathematical term for Pringles shape. It's not just aesthetically pleasing. It's structural engineering. The curve distributes stress evenly across the chip's surface, making it stronger than a flat chip, despite being thinner. The ridges add additional structural support through geometric bracing. A Pringle can support 8 pounds of pressure before breaking. A regular potato chip breaks at 2 pounds. The molds move through the station on a conveyor system. There are 4,000 molds constantly cycling through. Each mold forms 1 chip every 3 seconds. That's 80,000 chips per hour from a single production line. The factory has 12 lines running simultaneously. That's 960,000 chips per hour. 23 million chips per day from one factory. The precision is absurd. Every single chip has the same curve with a tolerance of 0.2 millimeters. The same 14 ridges in the same positions. The same thickness at every point on the chip. This consistency is why Pringles stack perfectly in the tube. If the chips varied even slightly in shape or thickness, they wouldn't fit together properly. The molded chips move directly into a continuous fryer. This is a 25-meter-long machine, filled with cottonseed and corn oil, maintained at exactly 182 degrees Celsius. The chips travel through on a conveyor belt, submerged in oil for exactly 11 seconds. This temperature and time combination is the result of decades of optimization. Too hot, and the exterior burns before the interior cooks. Too cool, and the chips absorb excess oil and become greasy. Too long, and they darken excessively. Too short, and they remain soft. The 11-second fry at 182 degrees produces chips with 33% fat content, golden color, and the correct crispy yet not brittle texture. The oil temperature is monitored by 47 sensors throughout the fryer. If temperature deviates more than 2 degrees at any sensor, the production line automatically stops. The oil is filtered continuously through a side system that removes particles and moisture. Fresh oil is added constantly to replace what's absorbed by chips and what's removed by filtering. The oil in the fryer completely turns over every 4 hours. But here's the part that makes this interesting. The frying doesn't just cook the chip, it fundamentally changes the starch structure. The heat causes the starch granules to gelatinize and then crystallize as they cool. This creates the rigid matrix that gives Pringles their texture. If you examined a Pringle under an electron microscope before and after frying, you'd see the starch structure completely reorganize at the molecular level. The chips exit the fryer and move immediately to a cooling conveyor. They need to cool from 182 degrees to 35 degrees in exactly 45 seconds. Cool too fast, and the surface cracks from thermal shock. Cool too slow, and they continue cooking from residual heat, becoming too dark and too crispy. The cooling happens in a chamber with controlled airflow that removes heat at a specific rate. Freshly fried and cooled chips enter the seasoning station. This is a massive rotating drum where flavor powder is applied. The drum rotates at 45 revolutions per minute, while seasoning powder is sprayed from nozzles positioned at specific angles. The chips tumble through this powder cloud for exactly 8 seconds. The seasoning isn't just sprinkled on, it's electrostatically charged. The chips exit the fryer with a slightly negative charge from the frying process. The seasoning powder is given a positive charge as it leaves the spray nozzles. This creates electrostatic attraction that makes the powder stick uniformly to every surface of the chip without requiring any additional oil or moisture. This is why Pringles seasoning covers every millimeter of the chip's surface, including the ridges and the underside. Regular potato chips are seasoned by tumbling in powder, which mostly sticks to the top surface. Pringles use electromagnetic forces to coat all surfaces evenly. The amount of seasoning is precisely controlled. Original flavor chips receive 2.8 grams of salt per pound of chips. Sour cream and onion receives 4.2 grams of flavor powder per pound. The seasoning application system weighs the chips before and after seasoning to verify the correct amount was applied. If a batch is over or under seasoned by more than 5%, it's rejected. Different flavors have different powder particle sizes. Salt for original flavor is ground to 80 microns. The powder for cheddar cheese is 150 microns. Barbecue is 120 microns. These sizes are optimized for how each flavor needs to dissolve on your tongue. Smaller particles dissolve faster, creating immediate flavor impact. Larger particles dissolve slower, creating longer-lasting flavor. After seasoning, chips move through an optical inspection system. High-speed cameras photograph every single chip from multiple angles at a rate of 1,200 chips per second. Computer vision algorithms analyze each image for defects. The system checks for color variation. Chips darker than the acceptable range are rejected. Chips lighter than acceptable are rejected. It checks for breakage. That chip is rejected. It checks for size. Chips outside the specified dimensions are rejected. These rejected chips fall into a separate bin and are ground up and recycled back into the dough mixing stage. Nothing is wasted. The rejection rate is typically 2 to 3% of total production. That means 97 to 98% of chips make it through quality control. At 23 million chips per day, that's still 460,000 to 690,000 rejected chips daily from one factory. These rejected chips aren't sold as lower-grade products or used for anything else. They're recycled because maintaining consistent quality is more valuable than maximizing short-term yield. Human inspectors also sample chips randomly throughout the day. They break them to test crispness. They measure thickness with calipers. They weigh them to verify oil content. They taste them to verify seasoning levels. Every production batch has documentation showing that it met all specifications, and this documentation is kept for 2 years in case any issues are reported. Chips that pass inspection move to the packaging line. This is where engineering meets psychology. The Pringles tube isn't just a container. It's a protective structure specifically designed to prevent chip breakage during shipping. The chips are stacked automatically by a robotic system that places them in perfect alignment. The stack enters the tube from the bottom, and the tube moves up around the stack. This prevents chips from falling and potentially breaking. The stacking robot can align 80 chips per tube in 2.4 seconds with zero breakage. The tube itself is made from a composite material. The body is thin cardboard wrapped in aluminum-coated paper. The top and bottom are plastic. The aluminum coating creates a moisture barrier that prevents chips from going stale. The plastic ends provide structural strength. The cardboard body is recyclable, but the aluminum coating makes it complicated, which is why Pringles tubes have been criticized environmentally. But here's why the tube design is actually brilliant engineering. Traditional potato chip bags are 80% air and 20% chips by volume. This air cushion prevents breakage during shipping, but it's inefficient. Trucks and warehouses are mostly transporting air. Pringles tubes are 90% chips by volume. The chip shape and tube structure protect against breakage without requiring air cushioning. This means more chips per truckload, fewer trucks needed, and lower transportation costs and emissions per chip consumed. The tubes are sealed with aluminum foil across the top and a plastic cap. The foil is induction sealed, meaning it's bonded to the tube rim using electromagnetic heating. This creates an airtight seal that keeps chips fresh for up to 15 months unopened. Traditional chip bags have a shelf life of 3–6 months. You might wonder why Pringles need to be manufactured this way. Why not just slice potatoes like regular chips? The answer is economics and consistency. Traditional potato chip manufacturing has 30 to 40% waste from peels, damaged potatoes, and inconsistent slicing. Pringles manufacturing has 4% waste. Traditional chips vary in size, shape, thickness, and quality. Pringles are identical. Traditional chips break easily during shipping, creating 15 to 20% loss between factory and consumer. Pringles have less than 2% breakage. But here's the real advantage. Stackable chips in rigid containers are more shelf-stable, ship more efficiently, and provide consistent eating experience. The manufacturing cost per chip is higher than traditional chips, but the reduced waste, lower shipping costs, and premium pricing offset this. Pringles are expensive per pound compared to regular chips, but consumers pay for consistency and convenience. The process also enables precise control over nutrition and ingredients. Every Pringle has exactly the same calorie count, fat content, and sodium level. Traditional chips vary significantly from chip to chip. This consistency matters for people tracking nutrition and for regulatory compliance in different countries. A single Pringles factory produces approximately 23 million chips per day. That's 8.4 billion chips per year from one facility. There are multiple Pringles factories worldwide. The largest ones are in Tennessee, Belgium, and Malaysia. Combined global production is estimated at 60 billion Pringles annually. To produce this volume, the Tennessee factory alone processes 200,000 pounds of potato flakes per day. That represents about 1 million pounds of fresh potatoes before dehydration. They use 180,000 gallons of frying oil per week. They go through 50 tons of seasoning powder daily. The factory operates 24 hours a day, 7 days a week, except for scheduled maintenance shutdowns 4 times per year. The entire process from potato flakes entering the mixer to sealed tubes, leaving the factory takes 26 minutes. Every 26 minutes, raw materials at the start of the line become finished products at the end. The factory is essentially a continuous flow system where materials are constantly entering, being transformed, and exiting as products. The precision and scale are what make this fascinating. This isn't artisanal food production. This is industrial engineering applied to snack manufacturing. Every variable is controlled. Every step is optimized. Every chip is identical to every other chip produced anywhere in the world. That level of consistency is what modern food manufacturing achieves. And Pringles represent the extreme end of that spectrum, from dehydrated potato flakes to perfectly curved, uniformly seasoned, identically stacked chips in exactly 26 minutes. That's how Pringles are made. Not from potatoes in the traditional sense, but from engineered food materials processed through precision manufacturing that treats every chip like a mass-produced component rather than a food item. And that's why they stack perfectly every single time.